So we continue with our next talk, again about codecs, this time about VVC, with two projects about encoding and decoding VVC. Please welcome Adam.
Hi everyone, so today I want to introduce you to VVenC and VVdeC. Those are open source implementations for VVC. Now, to pick everyone up about VVC. So VVC is this new codec that was finalized just over 2 years ago. And if you want to know one thing about VVC, basically VVC allows you to have the same quality as HEVC at half the bitrate. And on top of that, it was developed by the JVET, which is the Joint Video Experts Group. And it's called versatile because it's applicable in versatile scenarios, right? So we have support for screen content, HDR, as we heard in the previous talk, immersive, 8K, and we can do some fancy stuff like doing adaptive streaming with OpenGOP. All right, so now let me talk you through a little bit of the background of our projects, VVdeC and VVenC. So of course, those are both those are team efforts, right? They are developed by a whole team of researchers at the Fraunhofer HHI, mostly in the video coding systems group. Now, Fraunhofer HHI, if you don't know it, like modern video coding probably wouldn't be what it is if it wasn't for HHI. And HHI is part of a biggest European research organization, the Fraunhofer Society, which is a big German non-profit. And then about me, so I'm Adam Wiskowski. I've been at HHI since 2016, and I've been leading the project since 2019. And since about a year, I'm also the co-head of the video coding systems group. So why did we even start the software project? So basically, there was HEVC for which the test model was HM, and HEVC uses square blocks. So they had this method of indexing blocks within within the frames using this set index method, which is really amazing for square blocks. And then, they were exploring VVC based on the exploration model, which was still based on HM, except VVC supports rectangular blocks, right? So it's more than only square blocks, and there were really a lots of code for working around this set index thingy. And at HHI, we wanted to do even more than that. So we started work on our own partitioner, and we just decided that this is not going to work. And what we had to do, we basically had to write our own software to deal with it, which we very creatively named the Next software, which later became the VTM 1.0. And basically, the biggest difference is we had one big map that was mapping the position within a frame to like an object that was describing the current coding block. So the next software, it became the VTM, which is the reference software for the VVC standard. And you can see there in the graph how the VTM was developing over time with regards to the gains over HM, with the encoding time, decoding time. And here you can also see how we started our implementation projects from VTM. So from the VTM 3.0, super early, we already started work on the VVdeC. And then from VTM 6.0, we started the work on VVenC. Then in the early 2020, Benjamin Bros became my boss. We basically started the VCS group, and he brought up the idea maybe we can do the projects open source, which we did initially end of 2020 under a little bit shaky license, but with some back and forth with the headquarters, we were able to change it to like a modified BSD3 license, and after some more back and forth, we actually have an unmodified, like a standard open source license, the clear BSD3. All right, so let's talk some more about the projects. Some hard facts. So as I already mentioned, they are based off VTM. They are both written fully in C++, but we do have like a pure C interface, so you can integrate it into frameworks or just use it from a pure C code. Those are C++ projects, right? So they are object-based, but it's kept very simple. So we try to, not hide anything, no getters, no setters, and like have all the control over what is happening in the memory. Contrary to some other, some other projects, we do not do assembler at all. We do only vectorization using intrinsics, which of course has the advantage that we get stuff like ARM support for free through this amazing SIMD everywhere library. Also support for VASM cross-compilation, so WebAssembly, which we also did. And what we try to do, we try to make those projects as simple as possible. So basically, we only expose options that are use case relevant, but like the coding options, everything that's like connected to efficiency, we try to define it for the user to just have the simplest experience possible. Yeah, they're both available on GitHub under the BSD3 closed clear license, as I already mentioned. All right, so how do we do the development? So the development is done internally without HHI. So we have our own main Git repo that we basically, from which we push squashed updates to the GitHub repo. Why is it internal? I know many people find it out a bit, there might be issues with that, but here on the right you can see, or maybe you cannot see, a typical merge request that I would do on the internal stuff, on the internal repo, and I think this is just not something that is ready to be released to the public, so I would rather hide those kind of hiccups, and yeah, it just takes too much time to make stuff nice for being public. And I also think not everyone at HHI might be comfortable being like a public developer. But yeah, all of the stuff that we have internally, it eventually goes to the public repo, either for new releases, to fix bugs or issues. If we develop a big new feature, we would push it. And if someone was to make a large contribution, of course, to rebase the code. All right, so VVdeC, the Decoder project. So the highlights, it's fully compliant with the main 10 profile of VVC. Of course, give or take few bugs. So actually, it was supposed to be fully compliant since the version 1.0, but stuff happens, we find bugs, we fix the bugs, but basically there is no feature that is really missing. It's multi-platform, so it works on all the major OSs, and it also works on different architectures thanks to SIMD everywhere, as mentioned. So we have like x86 support, ARM. I also saw people doing builds for RISC-V. So this is very nice. Also, one thing I'm kind of proud of also is that from the first version, we have like a unified thread pool. So also something that was already talked about. So basically everything is, like all the tasks are collected within this one thread pool that just balances itself, right? There is like no frame threads, slice threads, which also means our multi-threading is independent of bitstream features, right? We don't need tiles, slices to be able to parallelize. So I think this is a really nice feature. All right, let's look a little bit into the development history. So this on the left is like the performance graph for different resolutions, different coding conditions, so like random access or all intra. And major milestones mentioned 1.0, full compliance with the standard. In version 1.3, we did a 3 times memory reduction, and I was also asking myself, how could we ever release any other? How could we have ever released any other version? But yeah, at least we managed to get it better. 1.4, we got a major performance boost based off external contributions in GitHub. So this was really nice to see. And in between, we really had a lot of small improvements. And as you can see in the graphs, it does add up. All right, about the VVenC. So VVenC, it's a Encoder project. Of course, it's way more complex, way more interesting. It has way more degrees of freedom, right? Like Decoder just does this one thing, and has 0 degree of freedom, right? Basically, the standard tells us exactly what to do, and the encoder has all of those choices that it has to do. Anyway, what I like to say is, it's basically the best open source encoder out there. As you can see here on the right, it's runtime versus efficiency. So, for a given runtime, we can have the best efficiency, and for any of our working points, we can get this efficiency the fastest. Of course, it's not the best encoder if you want to encode UHD live. We're not quite there yet, but and at those slower working points, it really doesn't get better than that. At least not that I am aware of. All right, so we have 5 presets on the encoder, from faster to slower. And you can see, this is a single-threaded graph. You can see more or less how those presets compare to x265 in orange. We have very efficient multi-threading, at least like between, up to 8 threads or with up to 16 threads with some additional options. I'm going to talk about this a little bit in 2 slides. And we have a very good optimization for human visual system based on the XPSNR metric, which I'm also going to mention a little bit later. We have really excellent rate control. So, with bitrate deviations, rarely more than 2%, and like almost never more than 5%. As I mentioned, simple interface, and it's, this thing can be used for academic, amateur, commercial uses. The license really allows it all. All right, so we have those 5 presets. How do we derive those presets? Like from an academical point of view, this is actually done in a very interesting way. So we take all not use case related options of the encoder, and we do like large scale optimization. So we start with a very simple, very fast working point, and then we try to derive which option should be changed as the next one. And this is always the option which basically gives incrementally the next best working point, right? And this is a huge optimization. It takes really a lot of compute time. So we don't do it so often, like every 2 or 3 versions. Or if we know one tool got implemented way better, we can like try to only optimize for this tool within the option space from the last optimization. We target HD and UHD, natural content, but we do sanity checks for our resolution and like screen content or HDR. And the one issue that we still have is, at the beginning here, you can see that our curve gets a little bit steeper, right? So we cannot go too fast because at some point, for like every 2 times speed up, we're just losing too much efficiency. This is because, we started from the reference software, which was designed for readability, and the efficiency is still work in progress. All right, about the multi-threading. So our multi-threading is also, I would say, done differently than in many other encoders. So we do the multi-threading over CTUs, so like the modern macro blocks and CTU lines. Like we simulate wavefront parallel processing without using the syntax. And we parallelize independent frames, right? If like 2 frames are independent of each other and the references are already done, we can do those in parallel. Which of course means that how much we can parallelize depends on the number of CTUs that are available, which are always more in high resolution or with smaller CTU sizes. That's why the faster and fast presets, which have smaller CTUs, they parallelize a little bit better, which you can see on the top right there in the full HD parallelization efficiency plot. Right, you can see like after 8, it kind of, well, it doesn't saturate, but like after 8 threads, there might be better ways to utilize the resources than to just enable more threads. Exactly, and how can we improve the scaling? So we can improve the scaling by enabling normative features of VVC. So either doing tiles, that is independent regions within the picture, or enabling the normative wavefront, which allows us to kill one dependency within the encoding. And this is on the bottom right. So you can see, if we enable those additional features, the multi-threading scaling actually gets much better, but it costs between 3 to 5% of bitrate overhead. But still, even with those added features, the encoder is not ready yet for more than, let's say, 32 threads. So like, if you have a really, really big server, the encoder will not be able to utilize all the cores. Yeah, and about our optimization for the human visual system, it's based on the XPSNR, which is this new metric that a colleague at HHI developed. It has a really high correlation with MOS based on some public data sets. There are publications you can look up. They're mentioned on the bottom left. And it has been contributed to FFmpeg as filter, and I think it is somewhere in the backlog of FFmpeg waiting to be looked at. You can see on the right here a lot of graphs. So basically in the last JVET the JVET meeting one before last, there was a verification test with actual human subjects, where where VTM was tested with like the new compression technology, and we submitted VVenC to be tested alongside of it in the slow preset, right? So the slower preset has around the efficiency of VTM. Slow preset is objectively 5% behind. And as you can see in the graphs, VVenC in orange matches or outperforms VTM, which means that our visual optimization is well able to at least close this 5% gap, if not even, add more in terms of visual, subjective visual quality. So yeah, that's really nice. All right, VVenC in practice, everyone asks in the end, so what kind of FPS can you achieve? So we did some encodes onto mobile workstation kind of computers, encodes using all defaults, which means 8 threads. And for HD versus live, it's like for faster, it's around ×4, like live ×4, so around 15 FPS, medium around live times 30. All right, so around 2 FPS. I'm talking about HD 60 FPS as live. For UHD, the faster can do like 15 times live, fast 30, and medium, well, let's just say medium would only be of interest for like large-scale VOD encodings, right? But FPS also depends on many other factors like bitrate, content, your actual CPU and stuff like that. So this is more like ballpark numbers.
Excuse me, is this HDR content?
It is not HDR content, but it's 10-bit. So it should be roughly the same for HDR. Yeah, like we only test with 10-bit usually. It works for 8-bit, but it's kind of 10-bit native. All right, also some version history for the VVenC thing, for the VVenC project. So our first major milestone was the 0.3, where we added frame threading, and you can see on this multi-threaded efficiency versus speed graph that it was, a huge leap for us. In the 1.0, we added pure C interface, allowing, the integrations into pure C frameworks. 1.4, scene cut detection. 1.5, we added like arbitrary intra-period, so it doesn't have to be aligned to anything. We added a fast decode preset, and in the newest version, the thing that I really like about it is that we added the ARM support. And every version we add improved ray control, thanks also to great community feedback. And from one version to another, your encode might be 10% faster, but if you had a ray control problem and it got fixed, it's gonna be like way better. So this is like this hard to quantify improvements are actually one of the most important ones. And you can see how the curve behaves. So extrapolating, I'm sure we're gonna get even faster and better in the future. All right, about the ecosystem and the community, of course, this is raw video encoding and decoding. This is really only of academic interest, right? Like, it doesn't really bring you anything. That's why we have been looking into FFmpeg support for a long time. There was an open access paper over 1.5 years ago that described how to do it for the decoder. There are some patches in the pipeline with FFmpeg. We also put in our wiki how to apply them manually if you want to build it. I know, I've talked about this a lot, but the thing is, if it's not in FFmpeg, it doesn't exist. That's why, we put up a how-to for you on how to do it. All right, about playback, once you get this FFmpeg with VVC included, you can just link whatever player uses FFmpeg as its backend, and it's going to work. As far as I know, for VLC, you might force it to use the FFmpeg as the demaxer. Not sure about it. Didn't test it myself. It comes from community feedback. I know there are some exoplayer integrations going around, which allow you to use it in Android apps more easily. We have a toy web browser example, but it's nothing like the VLC JS. It's really a toy example. And for maxing and demaxing, you can just use JPEG. Sorry, for maxing dashing, you can just use JPEG since the version 2.0, and I think it also needs to be linked to an FFmpeg with VVC support. All right, for community, we are open to external contributions, and we wish to get some. That's also why I'm talking to you, to we'll get some interest. So we try to make this more easy by stating that the authors of VVenC are also retain the copyright. We don't have like a contributors agreement, so this is like the only way we can make it happen. We are interested in all kinds of contributions, efficiency, speed up, and we're gonna thoroughly review this, test, generate result, whatever is needed, give proper feedback, merge. So yeah, please do if you're interested. To conclude, if you just enter the room, I talked to you about our open source implementations of the VVC standard, and I'm looking forward to contributions, also results, tests if you want to try it out, and general feedback. Thanks a lot.
Any question in the room? Yeah.
What confused me, because I know a little bit about the backstory, so H265, right, was
Yeah.
it super proprietary and had royalties, and the Alliance for Open Media launched the VVenC codec,
Yes.
and now your codec is open source and free, right? And
To recap,
will be, why is it H266? Is that related? Or?
To recap the question was H265 was a proprietary codec with licensing. AV1 is a non-proprietary codec. And then I'm talking about VVC, which is the successor of HEVC, so H265. And there is a small confusion. So I'm not talking about the codec as being open source. It's about the implementations of it, right? So you have to differentiate between implementations and the technology itself. There will be licensing for the technology itself, but there is still open source implementations also of HEVC. So that's kind of the way I would like to see it,
So it won't be like with MP3, where Fraunhofer also developed, it will be completely free to use for everyone.
No, it won't.
Oh.
I mean, the software is free to use, but if you build your streaming service based on the technology, independent of which software you use, you have to pay royalties for the technology.
Because you have patents. That's patent issues.
Yes, I mean, there is, this technology costs stuff to develop, and people want to get their investment back,
Okay, disclaimer, I'm doing CMD optimizations for video codecs in general. My focus is ARM, and my comment to you is using a library like CMD Everywhere works. It's going to give you the initial results that you want, but you will never get the optimal performance out of your hardware. We had some really good examples of code, particular algorithms like or instructions, intrinsics, move mask type of intrinsics that are very common and popular in Intel. If you try to port them with CMD Everywhere or some kind of abstraction layer to ARM, you're going to have to emulate this behavior. So ideally, you would have to provide some way to provide optimized functions for ARM or any other future architecture. Otherwise, you're just going to have your Intel layer translated to ARM. It will work, but you will never optimize your software.
So
the way you want
to recap the comment, there was a comment that CMD Everywhere works, gives a nice initial, initial deliverable, but will never match hand-optimized assembler. We are
not even assembler. C with the corresponding ARM intrinsics.
I mean, when I say assembler, I mean intrinsics. So we are aware of it, and we are looking a little bit of it. There are different kind of intrinsic kernels that are implemented there. Sometimes you have like 2 pieces of memory that needs to be added up and stored somewhere else. There, CMD Everywhere works really nice. But when it's like lookup tables, shuffles, it works worse. We are aware. We are looking into identifying the kernels where there's the biggest potential for improvement and doing those manually.
I'm doing HDR implementation of ARM of VPX. Okay, so I'm doing the ARM optimizations for that. And the way to do the transpose, for example, on 10 is completely different to the way Neil is doing it. Especially with, because for AVX2 you have 256-bit wide registers. You don't have that with Neon, but you have other instructions to help you tackle the outcome.
Yeah.
So my point is that if you are open to contributions with specific optimizations, then you might find people to help with that. But if you restrict yourself to only using the library and only use Intel intrinsics and then translate that to ARM using the library, you might lose some performance, a lot.
We are not restricting ourselves, to only using this. It's just because, we only have so many resources. This was the fastest way to do it. We can play it out on, like actually this thing can play out VVC videos with our software. But yeah, totally. I think there would need to be some changes to the build process, maybe to the structure of the project to enable this. But yeah, this is something really very interesting, and I think there will be a lot of research going on in that direction. Thanks.
One last question, yeah?
How does it compare? What are the advantages of over AV1 in terms of compression or computation?
Well,
Please repeat.
yeah. So the question is, what are the advantages of VVC over or VVenC?
VVC over AV1.
All right. So what are the advantages over of VVC over AV1? So VVC is the successor to HVC, right? It was done by people who were really knowledgeable on how to make a standard work. So it's the one thing. It just provides the additional bitrate savings, right? So here you still see like 20% additional bitrate savings over like the best case of AV1, and there isn't so many of these initial hiccups, right? So the HDR support just works, immersive stuff just works. A lot of those things, they just work, and then we can do stuff on top of that, like doing OpenGOP adaptive streaming, which allows you to reduce the bitrate by like another 10% on top of that, right? Like with all the other standards, I think the adaptive streaming can only be done with closed GOP, so with a prediction break. Basically, that I would say more mature, but I know there are different views of that. More compression efficiency, and really versatile, mature usability.
Thank you, Adam.
Thanks.